Hi, my name is Maddie Legg, and welcome to a lecture on energy in simple harmonic motion. Simple harmonic motion is defined as the motion of a mass in a spring when it is subject to the linear elastic restoring force given by Hooke's law. So just a summary of some of the things we'll get into. Hooke's law states that the force exerted by a string is directly proportional, varying with k, to the distance the spring is currently extended or compressed. This is basically force equals negative kx, where k is the spring constant and x is distance in meters. So position can be modeled with x equals amplitude times cosine of omega t plus delta. It could also be modeled with sine. A is your amplitude. And amplitude is the maximum distance that the spring reaches from its equilibrium point. Angular frequency is omega. Omega t plus delta is your phase constant, and delta is your phase of motion. When a mass is at a maximum distance, when t equals 0, delta will be 0 here, and the graph will be modeled by this cosine function. In the second graph, there is a phase shift of negative pi over 4, which is your delta. This indicates that the mass does not begin at its max distance. So it's starting out here, which is at 2, and then at time equals the period, or 1/8 of the period, it reaches this maximum distance. So it shifts the graph over, basically. Velocity and acceleration. So you can get your velocity function by simply taking the derivative of x with respect to time. So velocity in the x equals dx dt, which is negative omega a sine of omega t plus delta. To get acceleration, you do the same. So that gives you this lovely function here. And what you can do, since here x equals a cosine of this lovely equation, you can plug that in for this. That gives you this equation, which is acceleration equals negative omega squared times x. A nifty little proof to show that omega equals the square root of k, which is your spring constant, over your mass. So we know that force here equals ma, so ma equals negative kx. Move over your m, you get a equals negative kx over m. We can substitute in negative omega squared x for our acceleration. From here, the x's cancel, the negatives cancel, and you take the square root, and that gives you omega equals the square root of k over m. Period and frequency. So your period is the time that it takes to complete one cycle. This is measured in seconds. So, period, if here's a mass on a spring, and you stretch it all the way out and you release it. Period is going to be the time it takes to go all the way here and all the way back. Frequency is cycles per second, which is measured in hertz. So, t always equals 1 over f is always 1 over t. T can be found by taking 2 pi over your angular frequency, and f is just the inverse of that. So to find your maximum velocity and acceleration, we can take advantage of the fact that sine and cosine both have a range of plus or minus 1. So we can set those equal to 1 to find the maximums. So your maximum velocity is simply omega a times 1. We can substitute in square root of k over m for that. Same goes for acceleration. Set our sine equal to 1, or our cosine equal to 1, or whatever it may be. And you can also substitute in square root of k over m, and the square root and the square root cancel. So let's talk about energy in a system like this with a spring with simple harmonic motion. So when time is 0, the position is at a maximum, your velocity is 0, your acceleration is at a maximum, your force is at a maximum. kinetic energy is going to be 0, and your potential energy, which is 1/2 kx squared, is going to be at max. So in the second scenario, when we reach the equilibrium point, where x is 0, your velocity will be at a negative max. That means that your kinetic energy will also be at a max here. Your potential energy will be 0, your force will be 0, your acceleration will be 0. So when it reaches this negative max here, it's going to be basically the opposite. Let me get my pointer back here. It's going to be pretty much just the negative of this one. So your velocity again will be 0, your force and your acceleration will be at maximums. It's going to be all potential energy and no kinetic energy. Yeah. Same goes here. When it's returning and it's at this equilibrium point, these are going to be the inverse of each other. I don't know if I need to rehash that. And here is exact same as the first scenario, where here it's back at the equilibrium point, force is at a maximum, it's all potential energy and all that jazz. So potential energy. We know that position can be modeled with this lovely function here. And we know that your potential energy in a spring is 1/2 kx squared. You can substitute this in for that. That gives you this lovely equation, and when you square everything, gives you that. Kinetic energy, you can do pretty much the exact same thing. So we have this velocity equation, and we have our equation for kinetic energy, just 1/2 mv squared. You can substitute in for v, and distribute out that squared. Some more nifty equations. As long as there's no outside forces acting on the system, your total energy will always equal your potential energy plus your kinetic energy. And this, as long as there's no outside forces, this will be constant. The total energy will also equal 1/2 times your spring constant times your amplitude squared. Something that's really helpful here is you can find your velocity at any position by using this equation. So plus or minus omega times the square root of a squared minus x squared. So a 1.85 kilogram object on a frictionless horizontal track is attached to the end of a horizontal spring whose force constant is 4.82 newtons per meter. The object is displaced 3.43 meters to the right from its equilibrium position and then released, which initiates simple harmonic motion. So we want to find the magnitude of the force acting on the object 3.56 seconds after it's released. So our object's mass is going to be 1.85 kilograms. Our amplitude is going to be our max distance, which is 3.43 meters. Constant is going to be 4.82 newtons per meter. So we know that force equals negative kx. We know k, we need to find x. So we can go to our lovely equation for position, which is a cosine of omega t plus delta. And we know since time starts when it's at its maximum position, we know that this is going to go to 0. So we need omega now to plug in for x. So we know that omega equals the square root of k over m. That means that omega is going to be the square root of 4.82, pardon my handwriting, over 1.85. And that is going to give us an angular frequency of 1.614. So we can plug that back into here, and we have a time that's 3.56 seconds. So our x is going to be 3.43 cosine of 1.614 times 3.56. And that is going to give us a position of 2.947 meters at that time. Now that we have our x, we can plug back into here, and it's simply, our force is going to be negative k, which is, again, 4.82. times our x, which is this 2.947. So that's going to give us a force of negative 14.206 Newton. Another problem with 4 lovely parts. So we have a 0.2 kilogram block, so mass is 0.2, attached to a spring of force constant 13 newtons per meter, oscillates with an amplitude of 20 centimeters or 0.2 meters. So we need the maximum speed of the block. So we are going to go back to this equation, which is just omega times a. So this is going to equal square root of k over m times a. So this means it's going to equal the square root of 13 newtons per meter over 0.2 kilograms times 0.2 meters, which is going to give us a maximum velocity of 1.612 meters per second. Number 10, we're going to find the speed of the block when it is 10 centimeters from the equilibrium position. So we can plug right in to this equation, plus or minus, we need omega in here, the square root of a squared minus x squared. Velocity is going to equal plus or minus the square root of 13 newtons per meter over 0.2 kilograms times the square root of a squared, which is 0.2 squared, minus 0.1 squared. It's going to give us a velocity at 10 centimeters of plus or minus 1.396 meters per second. For 11, we want to find the acceleration at 10 centimeters, so you can plug right in to here. A equals omega squared x. So we know that we can plug in square root of k over m for omega, so this is just going to be k over m times x. So plug in 13 over 0.2 times 0.1, which is going to give us an acceleration of 6.5 meters per second. For the last part, we want to find the time that it takes for the block to move from 0 to 10 centimeters. So I'm going to come back up here. X equals a, and we're going to start out with sine because we're starting out at the equilibrium position, so at 0. Omega t plus delta, and since we know that we're starting out at 0, we can set delta equal to 0. So that means that we're looking for time it takes to reach 0.1 meters equals maximum position here, which is our a, 0.2 meters, sine of omega, which we know it's 8.06 for convenience sake, times t. From there, we simply solve for t. So that's going to give us 0.5 meters. We divide over equals sine 8.06 t. So t is going to equal inverse sine 0.5 divided by 8.06. It's going to give us a time of 0.065 seconds. And that's when it is going to reach 10 centimeters. And that's all. Thanks for watching.